Okay? So, what do we have by now? By now we have different type of features from different types of data, right? That one we discussed yesterday. So, we somehow learned how to represent image data, location data, and text data in different ways. We have feature vectors, and these feature vectors can be fed in some machine learning model. And that's what we do in the last lecture, lecture 4. It goes through 3 classes of conventional machine learning models that can either estimate probability or predict, basically can predict some class of the data. And we go through some examples like text classification and some toy example of image classification, which is of course doesn't work in the real world like this, but we discuss some features can be used to update to make it more nice. By the way, I got some questions just now regarding the data set for assignment. We have assignment for the 4th day. It's a data set that is provided. I guess I will put a link to here as well. Link to the data set. Actually, the link to the data set is, I think I can also write it down because some people didn't see it yesterday. So this is a multi-source data set that contains data from 3 sources, from 3 social networks. One is image-based Instagram, another one is Foursquare, and one more is Twitter. So one provides textual data, textual features, another provides application features, and third one provides the image features. All the features are already computed, so we just need to apply some machine learning stuff, merge the sources, and somehow present a solution in Thursday. I guess we will have at least 4 or 5 groups that can present these solutions, and then you can get valuable comments from the Professor Charles Sen, who is coming today. Basically, can evaluate your solution, suggest you something. So further, you can publish it, or we can think about collaboration, or wherever. Anyway, it's important to try the real data rather than just listen. So the link to data set is like this. NUS multi-source dot Azure websites .net. You'll find the data set itself, the papers that describe this data set, and do some preliminary work and so on. So on Thursday, the first lecture will be wrapped up by Professor. He'll talk about some current trends. That one for sure you need to come just because, yeah, this is quite a famous lecture, and basically he will wrap up this course, he'll give his opinion and so on. And after that, I expect you, these 4 or 5 groups that will form, to present your solution, give results, see the problems. Also, maybe you'll find some bugs in our links. That was a nice result, but I'm not sure. So just now I get some problems, some questions about the data set. First question was about the mapping. Mapping of certain types of features for Singapore region. So in particular, there was not matching of user IDs for different text features in Singapore. LIWC features and heuristically inferred features in particular. So if somebody come up with exactly the same problem, let me know, drop me an email, we'll try to fix it by tomorrow or something like this. If somebody found that actually it maps correctly, it's supposed to map correctly actually. So if somebody do it successfully, then please let us know as well. In this case, we person who cannot map, just try to map again. So anyway, we need to solve this issue because this data set publicly available. Actually, other research groups work on it as well. So by now, nobody is telling me that there is no some mapping. So maybe they didn't notice, maybe they didn't use it. I don't know. So did anybody try to map features from Singapore? Yeah, we tried, right? And it works well. Yeah. All the text features maps to the thousands of users. So yeah, I'll try by myself when I go back. So, but probably it's okay. So you may try to do London because for London you know it's for sure maps. If for London you also cannot map, that means a problem in your code. If it maps and problem in the data set. So it was the first question. Second question was regarding the content. The data set is presented in terms of features, in terms of data representations. Why are we doing this way? Because Twitter itself forbids us to publish the tweets, publish the actual content. This issue is related to the fact that user may forbid others to read some certain messages of these users. So I published something today because I have a bad mood. Everybody read, but after like half a year, I don't want somebody to read that I have bad mood on certain topic. So I'll either remove this tweet or delete this tweet. And this is my right. And if somebody will publish my half a year tweet before as a public data set and everybody have access to it, this will be a violation of my right. That's why Twitter don't allow to do this, but they allow to publish the links to data set. However, those want to collaborate with our groups, so we have official collaboration, we have meetings, we do some research project, publish papers. For those ones, of course, we can provide this data with certain restrictions. And then you can do whatever analysis on the road, Twitter data you want, and you come up with any solutions, and we were happy to do this actually. We have collaboration with some Russian groups. We encourage people to work on it because it's a new field and it's quite interesting. So this is a link, right? Any questions, please ask me today, tomorrow during conference, any day you need me, or you can drop a mail in here. Any other questions regarding the data set right now? So those ones who didn't try data set, please try it till the end of the lecture, so maybe you'll get questions. The final aim is to predict the attributes. Attributes include age, gender, occupation, relationships, based on multiple sources for 3 geographical regions, for 3 cities. So, in this lecture I will talk about source fusion. Why? Just because we have different feature vectors. And what we're supposed to do is it. One feature vector describes user from a view of images. Another feature vector describes it in terms of text. And then one more in terms of location. And is it data similar or completely different? How is the nature of this data? It's obviously very different. And in fact, there is some research when people talk about it. They try to discuss all the correlations between the data. Very often we enclose different information, different behavior in different networks, depends on the purpose of the network. The example is just like Facebook, where we can share very private things to our friends in our private messages. Twitter, which is a microblog, where we can say a lot of different stuff, enclose our emotions, publish with an interest, so it's very public. And one more extreme is like professional networks, like LinkedIn, where we really care what we write and how we write. So we may not say, reveal too much about ourselves there, but at the same time the content will be very structured and very nice, so it's easier to process. And it's only text. And then we go to image services, which is just images. And actually, it's not images of us, it's images of something we take picture, right? So we can represent these images by image concepts, distribution, as in the last lecture. But we're not sure how to integrate it together with text, and then we get one more, the location data, and we also don't know how to integrate it. That's why we need to think about source fusion approaches that will balance all these data sources to come up with improvement of the final result. This is some references. So the first one is experiments regarding the boosting. Basically, it's like the boosting. Boosting is a thing that I'll explain later. It's one way to enhance the performance by playing with the data. And another one is a paper about combining classifiers, different ways to combine classifiers. The recent trend is actually jointly learn the weights of the classifiers. I guess I won't cover these techniques here today because I probably need one more lecture, two more lectures for this. The idea is similar. So if in a simple regression we will have something like wx minus y, and y is just a common vector. So suppose I have different sources, so every source has its own y, its own label. So we actually can do so-called multitask learning. Then y will become a matrix. And then w also will become a matrix, so we will learn weights for each source. And if we will regularize it somehow, like this, at least like this, and so on, so on, so on, and optimize it, we theoretically get the joint weights for each data source, and yeah, and it will help us. But this one we can read in the recent papers, the state-of-the-art approaches is called multitask learning, lasso, logistic lasso, and so on. These models are very popular now, so all people modify, play with it, and try to get better performance. So I will talk about other types of combining sources that are all mostly heuristics. But however, all these heuristics actually give very nice results. And actually, in all these competitions of image retrieval or classification or something, very often the best approaches are actually based on some ensemble learning methods, some heuristics, just because it is able to handle some nonlinear relationships. And we don't really know how to explain why it works, but it works and it works the best. It's very often works the best. So let's talk about data first, very fast. We have different type of knowledge, and all this data come from different sources, textual sources and image sources, and different. One of them are very structured, and others microblocks is completely rubbish. You still need to process it. So in Twitter, it's like this, and we have another variant of Twitter, like Tina Weibo, which is actually more popular than Twitter. It's a copy of Twitter in China, and so on, so on, so on. It's very social. People retweet, and one of the key aspects is the messages are around 140 words. That's very short. So all these conventional techniques to process actually doesn't really work. Another one is community-based question answering. This one is quite structured knowledge, you know, the mappings of questions, types of questions, types of answers, and so on. The good thing here, you have a lot of ground truth. For example, for healthcare, we often have communities when professional doctors reply to patients, and these replies are highly relevant to their disease, so there is some research in our lab which is aiming to retrieve these questions and suggest answers to questions by other doctors. So, for example, if your question is similar to somebody's else question that we already have in the database, we may give you quite a relevant answer by a professional doctor, just by retrieving this answer, and so on. So it's very structured. This is quite nice thing here. And we have blogs, which is more structured than microblog because it's filtered before publishing. The person prepares it for publishing. So I guess it doesn't have too much slang and so on. And we have Wikipedia, which is also a blog, in fact, and it's really structured knowledge. In fact, people even leverage on the text that Wikipedia uses to structure content inside, use it as a feature to classify the text of Wikipedia and so on. And they also have image services, which is Instagram or Flickr, which is kind of similar, except Flickr is supposed to be used for more professional users. And you have this much types of features I explained yesterday, which is color, shift, visual concepts, color moments, edge distribution, and very popular conventional deep learning features when we have some neural network like Google net architecture. We feed in image and we get something in output. And nobody knows what is something, but this something is so nice for predicting our label. In fact, deep neural network stuff is most of the cases now the best for image retrieval. But it's important to know how all others work because at least this one is explainable. That one is everybody just create one more randomly and then hope well. That's how they publish papers sometimes. Another one is location-based social networks. It's like Foursquare, Gawala, or Facebook, where people share locations and they can get not just location itself, but also value semantics, which is very interesting. You know the place where a person goes. And we also have different sensor data. There are first social networks that share sensor data. For example, MyFitnessPal, when people post information about their activities, about calories they spend, about calories they eat, and about their weight, and so on, so on, so on. So it's very interesting to analyze how their physical parameters change based on their calories intake, for example. And if you manage to map these guys to other social networks, you can get a lot of text. And you can map the text and physical parameters. There's a research group in Qatar. They basically do this research. They are focusing on correlating, for example, obesity in US with the social media indicators of obesity. And they say it's like 90%, 0.9 correlated for certain states. So basically, Foursquare, the places where you visit, is super correlated to how fat you are in general in terms of country level. So maybe it's interesting to get the personal insight.
Statistically significant.
Yeah, it is statistically significant, of course. They have a very big number of users, like hundreds, thousands. 100,000 users.
The significance is less than 0.05.
0.05, alpha is 0.05. It's okay. I mean, it's not 0.01, but 0.05 is okay. Yeah, I mean, they're social scientists, they know statistics stuff. They won't publish something really bullshit. So they usually try to make it reasonable. Yeah. So yeah, and we have all these sources, and the sources are of different types. Here's the textual sources, so we have other types of sources. And we need to fuse all of them together to get some model that can leverage on all these sources, balance them, and get the better results than in each individual source. That's basically our task. And it's a very interesting research problem. And in many fields, people do this. They do it in social media like you do, they do it in computational wellness, and even in image processing, as they try to detect tumor cancer in different types of images, like in MRI images and other type of features. So they need to merge this very multimodal, multi-source sources together to get the final result better than each source individually. So it's a very important task. If we find some nice, fast approach to do this efficiently, then it will be a bomb. I mean, everybody will cite this paper, everybody like it. Unified approach, lasso and multitasking is one of them. Other approaches. So the simplest way is so-called early fusion feature combination. What is early fusion? Do you know what is early fusion? It's a fusion that happens early, right? Yeah, and in fact it's like this. It's a fusion of features that happens early before the actual classification. And what it means, we have one source, another source, and one more source, which is very blur, but it's okay, there's one more source there. And they all fused in vector like this. So we get one more vector. So which problems do you see here?
Sources are equals in weights.
It's one. So we don't differentiate them, but they are very different. So what other problems do we have?
Dimension.
Correct, that's actually the biggest problem. It's quite often it's very big dimension. What else?
What if sum is missing?
And this is another very big problem.
Replace
So-
with
So what many recurrent research do is don't tackle the source fusion problems. They merge all together and then they say, and we do non-negative matrix factorization, which complete our sources, and then we're done. We can use other models. But this block mice missing data happens all the time, and I don't believe there is some linear algebra, simple stuff can just complete all these features so easy. In fact, like matrix factorization is just like decomposition of the feature matrix on another two matrices of lower dimension, and then you can map it back and complete features in this way. It's something very simple, and I don't believe that just by doing this you can complete everything together and make it work very well. So early fusion is not always work very well, and the number of features is too big. It's really too big, especially when you work with images or work with back-of-worst models or in grams and so on. But by the way, for image retrieval, if you combine shift features and local binary features and edges and the color histograms all together and do some concept learning on it, it's actually work quite well. And it's actually how we did it. So it's not always really bad idea for some really similar features that are all about image, one about edge. It actually works okay. But for some other domains, it's completely ridiculous to do this, especially for multi-model, multi-source fusion. So, and as we mentioned, yeah, we have this course of dimensionality when we have the drastic decrease of the performance of classifiers after a certain number of features. And even if you want to use this big feature vector, you actually need to have enough data samples to do this. So, yeah. So we need to handle it somehow. But in practice, we have a fixed number of training examples. So then we try to publish it, and then we are surprised why it's rejected because it's overfit, it will not work. So the course of dimensionality problem can be solved by some easy techniques. What in fact we do, we just remove features. So again, it's like feature selection approach I already mentioned before. So feature selection can be done by two ways. First way is just select those features that are most representative, for example, by its mutual correlation or correlation to the final label you're going to predict, especially if you use probabilistic models. Another one is different models like PCA, which is based on eigenvalue decomposition, or LDA, which is I was explaining yesterday, which is static modeling. They basically try to map our features to some another space, and probably this space will be, each feature in this space will be more independent A first, and second it will be probably high level. So it's basically an automatic way to map our low level features to some high level stuff, and this high level stuff will be, each of them will be more independent and generally be more representative. So it's two ways, right? First, just remove features that we have by using correlation, for example. Another way, map it to something else that may be better for us to use in a smaller dimension. And then we train our classifier based on this feature set. So since we have early fusion, we also have late fusion. What is late fusion?
When you fuse it later.
Exactly, yes.
When you use classifiers or algorithm used to process it.
Do you know any other types of fusions except early fusion and late fusion.
Somewhere in the middle maybe.
It actually doesn't have name, but again, this type, right? This type of cost function actually can help us to fuse them jointly during training process, because you have different labels. Here you have the samples in rows and labels for each samples from different sources and categories in columns. And then we jointly will jointly learn W, and dimension of W will be number of columns like this and number of rows like this, right? So it's actually very simple. So this one is called joint feature learning from multiple sources, and this is middle fusion kind of. But this one is not like very well developed, so people are working on it now and they publish new papers. So if you want to work on it and your maths is not too bad, so you can actually come up with nice papers and you can publish it quite good. We'll talk about late fusion. And late fusion is ensemble learning. Who knows what is ensemble learning? I guess some people also know what is going to raise hands. Okay. Yeah, ensemble learning is a very easy and yet very, very popular technique because it surprisingly will work very well. So we select some collection ensemble hypotheses or models and then combine them together, combine the prediction results. Just like I mentioned to you, right? If you have some outputs of classifiers, you can actually combine them by perform some simple techniques like voting or something. So, for example, we can generate 100 different decision trees from same or different training set, and then we can make a voting between the decision trees. So, how do you think what is better to generate from same training set or from different training set in terms of voting? No, of course, from different, right? Because if you generate from the same, then decision tree will be similar with similar results and nothing to vote. Decision trees actually have a problem. They really heavily overfit data. So decision trees must be used in ensembles. It may help to reduce its bias, reduce the difference in results. So it may come out with some nice general answer rather than just use independent decision trees. But they work good for small data, so that's an advantage. So we can reduce the error rate, and if our ensembles, if our models in ensemble are strong, then ensemble will be likely to classify everything very nice. And we can now have also weighted voting, right? As we mentioned before. There will be more voted samples based on its weight. Not based on the okay, we consider weight of the sample during the voting process. Voting is can be derived as like a linear combination of confidence of classifiers, for example. For example, we have some naive Bayes classifiers which observe some probability confidence that this is this result, and then we can just combine all the probabilities of those classifiers which are confident in these results and probabilities of another classifier group that are confident in another result. And then to do it better, we just weight each of these classifiers. How to determine weights? Well, first, we can learn it from data, right? Second, we can visually found it. In fact, in ensembles, it's not a big problem to find the these weights just by forcing, just because our classifiers can be like 10 or 5 classifiers. Just go through all combinations with some small step. So it's kind of nonlinear case, nonlinear combination, linear combination of linear models which give us nonlinear output and nonlinear overall model. And we hope well. So you have this training data, and we split this data to different data samples. This data samples can be completely independent, or can be so we can use see the intersection of sets in different data samples. Then we learn learners from each of these data samples. We get the models of each of them, and then we have some model combiner. Model combiner is some heuristic that combine all the models together, so voting or something. And then you'll get the final model here. This final model is supposed to output nicer results. So when we combine multiple independent and diverse decisions, we can get, and each of them have to be at least more accurate than random, of course, because if it will be less accurate than random, actually we highly likely to get even worse results as a result. Then we have a good probability to get correct decisions. So example is like this. We want to do the weather forecast. And the reality is like this. It's a binary, right? It will be nice weather or bad weather, which is smile and cloud. So one classifier outputs something like this, and it's wrong in these cases, right? Another classifier will output something like this, and it will be wrong in these cases compared to reality. Then one more output something like this, and then one more output something like this. And this guy actually quite correct, but it's not necessary he be correct. And we don't know when he will be correct. And then we will output one more, this one, and he will be wrong in this, right? So you see each of classifiers actually do some mistakes, right? So if we use them independently, we may not predict the forecast well. And then if we just take the majority vote on each row, here we will take smile, here we will take smile again, here we will take cloud, here we will take cloud, here we will take smile, smile and cloud. The final result will be just like this. If you combine, you get cloud, here smile, here smile, here cloud, here smile, here smile. And it's exactly as reality, right? So it's example of, in the case, artificial example, of course. It's example how ensemble of some somehow weak learners, right? We get only 3 out of 1, 2, 3, 4, 5, 6, 7 out of 7. 4 out of 7 correct, so a bit more than half. So it's all weak learners, but it can give a nice result. So this is intuition. So suppose we have 5 classifiers, and then according to the binomial distribution, we can estimate the percentage they will give us correct results. Of course, if each of these classifiers have a 70% accuracy. I guess everybody knows what this formula is, right? This information theory very classes. Anyway, it's like there's binomial distribution there, you can see it. And it's quite convincing because if you get 100, you'll get almost 100% probability that you'll get all the correct. And yeah, and of course, if our classifiers are less than 50%, we may get even worse results because they will bias each other. So another one way of thinking is enlarging the hypothesis space. So we can have different expansion of classifiers. For example, we have the ensemble of classifiers, and we decide that correct one in highly sensitive to accuracy task, we decide that correct results only those ones that are accurate with all 3 classifiers. One hyperplane like this, another like this, and like this. So we combine them together. Those ones who are confident in all 3 will be in center. And in this case, we will get high accuracy or recall. High precision or recall. Think about it, I will ask later. I think it's actually very nice. Yeah, and yeah, we have different learners, different algorithms, and you have different choice of parameters for these algorithms, like kernel function for example, or some hyperparameters for distributions that we use for LDA, for example. Often better actually don't know, number of topics also don't know. We need to estimate somehow. We have different data features, and we have different data set which consists of subsets. So we have ensemble with multiple learning algorithms, and we have these learners give us model, and then we can use majority voting or weighted voting to get the result as a wrapper. So then we combine them somehow and get the final result. So what is a majority vote? Well, this is very easy, we already discussed. You just see all the results, like an example with the clouds and smiles, and pick up the most popular label among different combinations. If you do it in a weighted way, then we have the weight, and we don't pick up the most often happen, but we pick up those ones that are most confident somehow. So I can read the slide later, I won't stop it. The idea is very easy. It's like an election. We vote for some candidate, and those ones who get the most votes will win elections out of the rules. The same is here. And yeah, it's supposed to be the living country better, right? So it's our assumption here. It's supposed to get the better results classification. So voted majority, weighted majority vote is the same thing but with a waist. So it's a decision for class WK can be represented in this way. And yeah, of course, we can normalize the coefficients to 1 for convenience. And what is interesting, there is a theorem. Sorry, I didn't put paper where it is given, but I guess you can drop me a note and I'll send you one email or upload to the page. That actually, we have L independent classifiers, D1 to DL, with individual accuracies P1 to PL. The output of this classifier can be combined as weighted majority vote, where weight is can be defined in such a simple way. Accuracy is a number of correct classification out of whole. How many times we correctly classify some data. So the weight in ensemble in weighted voting would be like this, and this will be kind of optimal solution. Yeah, I guess I need to put this paper here, so I'll put it later. I think I'll put in slide because that one I can upload too. So and we have homogeneous ensembles that play with different learners. So all learners are the same, but data is different. Or we can actually play with heterogeneous ensembles where data is the same, but learners are different. So we can combine different models of the same data, or same models on the different subsamples of data, or different models on different subsamples, which is combination. And we will discuss bagging and boosting. How many of you know what is bagging and boosting? That's good. Yeah, so bagging is very easy. The basic idea is we take subsamples of data with replacement and try and classify it based on these subsamples. So you can actually see the whole article. I take this figure from this article. So how it works for 1TL, we have a standard data set D of size n, right? So we draw sample size, some samples, and the size of that subsample is more than n, of course. And we can draw it uniformly, for example, we can do it uniformly with replacement. So different learners partially will get similar sample, partially will get different samples. And then we just combine them back together, and final classifications, classifiers will vote So that's supposed to help and actually help a lot, such as equal technique, just dividing the data. And it increases the stability of classifiers and reduces the variance. So it's quite useful. So it decreases the error by decreasing the variance, and it's good for unstable learners. For those learners that are weak and that are easy to change the decision. So since many of them may be too biased by some features or parameters, the majority of all of them are supposed to get some common conclusion, and that common conclusion will be better than each of individual outputs. But for KNN, for example, you may get some degree of performance in case of good data, and in case in simple situation when our learners are very strong. So what is weak learner? Weak learner is basically the classifier that produce some results that is a bit higher than random. Of course, 0.5 is for the binary classification, right? So it's correct in 50% of cases. And in fact, it's very difficult to construct strong learners. The whole our evaluations in our papers is about evaluating new strong learners or even new weak learners that are better than previous strong learners or weak learners for current applications. But a good news are we can construct weak learners, and this can be done relatively easy by a couple of clicks and some simple approaches. So can combination of weak learners actually give us a strong learner? How to see? How to see? Huh? Yes, of course. Otherwise, I won't ask for it. Yeah, and that's our idea. We need to boost the weak learners to a strong learner. And and strong learner is basically our objective, right? So we try to build a strong learner, and that can be arbitrarily accurate. A weak learner is something that we deal with, and it's a bit more accurate than the random guessing, but it's already nice enough for us. So, idea of boosting is somehow similar to bagging, but if in bagging we work in a sample level, in the boosting we will weigh the features and also the samples. Yeah, okay. In boosting, in the original boosting, we actually weigh the samples as well. Yeah. So the point is we have some weak learners. Yeah, by the way, this algorithm that was at the boost, I guess it was the most famous one by now. Famous one. The old and still work very well. And the key insight here is we reweight the examples. And each iteration, we change the hypothesis. We make a new hypothesis from what is learned. And then we still do the weighted vote. But yeah, our algorithm, the pseudocode looks something like this. Idea is very easy. We train on some sample, and then we see which samples actually influence the performance. Which of them, by learning on which samples, the final performance decrease. So which data samples are good, which data samples are bad. And then we weight those data samples that are bad with lower weights, and the samples that are good with higher weights. So it's kind of selection of nice data from the whole data set. And then finally it becomes ensemble learning again. So we construct classifiers in this block, and then we combine with learners in the end by logarithm reverse proportion of the weight, which is combined here. I can go through the slides at home and see the time again already. So, and there's actually many types of boosting and many types of weight we can do, and many different types of weighting schema, but the idea is always the same. We kind of select subsets of nice data and we train this. while in begging we randomly select this data. Okay? So, idea is like this. We start with uniform weighting, and then we increase weight for those examples which are not correctly classified, and decrease weights which are correctly learned. Or can be actually opposite, depends on implementation. So we are focused on learning from difficult examples which are not correctly classified in the previous step. Because it's not a big deal to learn based on easy samples. But we need a good diversity, so we focus on those ones that are complicated. And we combine all the three classifiers in one and get the idea. So the point is that the V classifiers gets a larger weight. And then they just work together, so that's explained. So here you can see the different data subsamples. So classes correspond to misclassified examples and crosses. You can see here, I'm not sure, can you see or not? Some of these are crosses and some of them are ticks. So ticks are the correct. And then we weight them. So bigger picture of 3 means you get bigger weight, and smaller picture to get a smaller weight. And finally we combine them together in one sample. But of course, if a weak learner is less than 50%, we may get in trouble because it actually increases performance. And there is one more research in our lab I made recently. The person was busy with the ranking, and he found that in task of a ranking is a similar issue. If you do a ranking, but initial ranking is worse than certain level of accuracy, the re-ranking finally introduces even more noise result becomes low. So all these combinations, combination stuff is basically based on assumption that our weak learners are not too weak, are not too weak to stay with. They at least give something more than random. Finally, we get the strong. Hopefully, we'll get a strong classifier at the end. Okay, so one more very powerful and yet actually state-of-the-art approach that I encourage everybody to try as a second step of their research. Because if you do better than random forest, then your model already not too bad. Yeah, so I suggest you to try random forest. How many of you know what is random forest? Oh, that's nice, more people. Okay, so, and of course, each of you know what is decision tree. Decision tree, I guess I already go briefly before, it's just can be expressed as a number of rules in the tree structure. We traverse this tree and go to the final assignment of category, actually even regressions for regression trees. So the idea of random forest is take our data set and do bagging. First we do bagging, and we split the whole samples in subsets with replacement. And then we do one more bagging, but in terms of features. So we use random subset of features in some inside each tree. So how it can help us? Why we use random subsets for each tree? For which task can it help us?
Different data from different sources and different trees.
Yes, possible further step. Yeah, that's what you can try in an assignment, maybe it will help. But basically, the whole idea here is, since different trees have different combination of features, some trees actually could become really strong because they may be likely to get nice features. So random forest incorporates the feature selection inside itself. And if we, okay, of course we need to know how many features we need to use for each tree, how many samples we will draw for each tree, but generally it's fair enough to say that if we introduce this double randomness inside random activity, quite likely to get really nice trees. And these nice trees will finally incorporate in the overall performance, and when we weight the whole ensemble, get good results. So, in fact, random forest is state-of-the-art classifier. So, I guess if you have random forest somewhere in your evaluation, and you manage to outperform random forest, it's quite good results, because random forest quite often the winners in different competition based on some nice features or somehow like this. Problem here is only it's not linear yet, so we don't know how to explain why it works. We only can see it works. We can evaluate it somehow. So how to select the n, the number of splits of data from data samples, and how to select m, the number of features will be used for each tree, and nobody knows. They can perform a grid search or they can do many other ways. But hopefully it helps. You can do it based on cross-validation for the one. The advantages are like this. One of the most accurate learning algorithms that are available now. It runs efficiently. You can handle thousands of input variables, so it doesn't really suffer from cross-dimensionality. Just because we'll still use trees, and each of these trees will have a subsample of features. Subsample of features, subset of features. So it will not suffer by itself, so each of them don't suffer, and the whole thing doesn't suffer from cross-dimensionality. And it actually can give us insights about which variables are important, and can give us estimate of generalization errors, and it maintains accuracy, even in the case where some data is missing. So I promise you that I will give one algorithm that actually can handle the missing data. Yeah, there is missing data, just don't use this record with some missing block for certain trees. Build another trees from this data. And then for those records that have that block, we will draw from the features as well. So it's kind of very easy combination. If you have some blockwise, if I write here, you can see we have some blockwise missing features like this. So some trees can be built. We can build one tree from these features, and then another tree from these features, and then another one from this, and then various combination of them as well. So it's very naturally handle this problem. Don't need to care about this. So I more believe in these approaches rather than just perform some matrix completion and do that very easy. Yeah. But there are some disadvantages here. It's actually may overfit in some noisy classification regression tests. Why? Because it's based on trees, and trees are often overfit. And also some data with categorical variables. If some categories will have big variation, others will have small variations, it tend to be biased to that category that has a big variation. Can you tell me why? Yeah, maybe you think about it and you can discuss it. It's not quite obvious. So and we need to consider some issues because all these ensemble learning approaches, they actually can be parallel. So we can do it much faster. And we have different variants of boosting to handle noisy data. And what should we use? What is this learner for boosting? When I say we have a boosting, I say it's some learner, but this learner is some machine learning approach. Which learner should we use? I'm not sure. So maybe it's another issue to consider. And maybe we can actually combine boosting and tagging, right? This actually makes sense. Speak on subsamples and then learn weights inside these subsamples, and then do ensemble. Maybe it actually can help. I'll go through evaluation measures very fast. I guess all of you know some of the evaluation measures. So they're supposed to care the efficiency and effectiveness, right? So we have some relevant, so we have basically 4 categories, right? Category A, B, C, D. If something relevant and it is retrieved, and if something not relevant that is retrieved, something relevant but is not retrieved, and something not relevant but is not retrieved. I also call it true negatives, true positives, false negatives, false positives, and so on. Different codes. This one is in terms of information retrieval, but can reformulate it in terms of classification. It's exactly the same. So we actually use precision and recall to analyze both information retrieval tasks and classification tasks. Because identifying the correct class can be considered as retrieval relevant document, and opposite classifying to incorrect considered as retrieval relevant. Okay, so and it's reasonable to combine them in one, because one of them talk about how accurate we are, how precise we are. Another talk about how much relevant data we collect in our output. How to analyze both? Yeah, we can use this something called F measure, and by popular version of us is F1. So basically it's called a B measure. So F1 measure will be computed as 2 precision recall based on its sum. And it's quite nice matters. Another one is you can build the graph of precision over recall, and then we can compute the integral area under this curve. This is another popular metric, how to combine precision and recall at once. And we also can present these results as like average F measure, for example. We can compute F measure for one category, for another category, for all of our categories if we have many, and then we can average them and we'll get average F measure. Or we can build the recall precision graph, so we can name number of, so like a table of, in which case precision grow, recall, drop, and so on, so we can analyze the results. So not only by one measure. And it's actually important, and I mentioned a data set that I want you to present your results based on assignment. In assignment, I want you to present results in a macro measures, because it's more fair measure compared to the micro one. Micro one is tend to favor the categories that are popular in data set. So for example, if you predict age, you have some popular age groups like 10, 20, 20, 30, and some not popular age groups like 40, 50. So if you are very good in predicting 10 to 20 and 20 to 30, but completely not good in predicting 40 to 50, which is actually interesting to predict that category. See, micro value will give you quite good performance because you will compute the overall, you will compute the precision overall, all categories. Macro measure will compute precision for each category. How well you predict 40, 50, how well you predict 30, 40, and so on. And then at average. So even if one category, the most complicated one, you are doing not well, the whole thing will drop your performance a lot, and that's fair enough. I think that's how people should compare their approaches, because our data is always, almost only in all the cases, are unbalanced between categories.
What's the difference between micro measure and accuracy?
Micro measure and accuracy. Actually reformulated that there is no difference between macro recall and accuracy somehow. There is no macro accuracy because you cannot compute accuracy through the whole categories.
So, if you are talking about micro measure, then there is no categories, all just documents. So we really don't care how the classes are, parts of the classes, how do they compare. So I think, so I'm not very sure if you can remember measure formula and can divide it, but it looks like that if we do it here, we'll just but how can you relate the measure for each document? It's like if you measure
No,
for
you
each
cannot do for each document, you calculate for each category.
no, but please put the next slide. So there is previous one. Micro measure is average of F measure over all test documents. So it means that you estimate F measure for each document.
Yeah, I think it's not correct formulation. It's a measure for each category.
But what's the difference between micro F measure and macro F measure?
I guess micro if measure is the if measure is that is computed. Oh, okay, I got what you mean. Yeah, macro if measure is just you just divide the if measure for each category by n. In micro if measure you compute. Yeah, it is kind of accuracy. Yeah, you're actually correct somehow. Because you compile the overall performance on local categories and you favor also on them. Yeah, it's correct. So, and we have also the average precision, which is number of relevant items is not known, right? So we don't actually know how many relevant items, like in information retrieval task, right? We retrieve something, but we don't know how many we have. So yeah, so we can use this formula. We divide the precision k to the relevance of this k, which is binary, is it relevant or not relevant, and we divide it by number of retrieved documents. So it can be computed in this way. So precision at k will be second line, right? We divide every time. Yeah, correct. So it's a position. The denominator is a position, right? So we can finally compute average precisions like that. And we need to divide by 4 to normalize it. And then we can get the average of average, and we will get MAP, so mean average precision. And there's other methods called DCG and so on. Quite many. All of them used for certain tasks, and sometimes people play with these metrics. If they not perform well for one metric, they publish another one. Sometimes it's important to use the same metrics as people use in data set. So the research that we were doing in data sets that I'm proposing you as assignment is macro recall. So I want you all at least to evaluate macro recall and generalization. Another attributes we can do something else. At least macro recall for all these two categories is important. Then you can compare. You do something very well. Okay. So, and we will talk about one more thing, which is popular. This can be used for first evaluation your data on a whole data set, evaluation your approach on a whole data set, and quite often this one used for estimating of general performance of your approach. So this general performance can be rather than used for weighting, for example. So you can do something that's called cross-validation, get some number of performance of model on this data in average. And then you can use this as a base to combine the final classifiers. So the idea here is like this: we split the original set of examples to train and test. And then we evaluate hypothesis in a testing set. We see the result. And then we change this set, so it will look like this. This will be, I guess, threefold cross-validation. First, we train on the green area and test on the gray one. Then we will train in another green area and test on another one. And then we will train in these two and cross in the last fold. So it will allow us to compute the average performance in a different subset. So in particular, this is the result how we can evaluate ourselves in the competitions. Because in the competitions we usually develop some approach that that allow us to predict some test set. And this test set is not unknown to us. Till the very end, when the organizers of competition will release the test set, we actually know our real results. So before that, what we can do, we can split our training data in this way, on train sets and test sets, and see if we split in different ways. Will our performance in the test set every time will be similar? So if it will be similar every time, it means our model, well, if it only similar, it means it may overfit. So our aim is to get the similar results. Extreme case will be once this leave one out, cross-validation, and we always take one and train on all the others, and compute how many times we classify this one correctly by training all the other data. And to summarize, it's very important to merge data sources together to leverage on the jointly leverage on all the data sources except on just one source. And it's very crucially important to merge sources efficiently rather than just linearly combine them in a very simple way, or just do some early fusion, which cause some problems like course of dimensionality. Yeah, and feature selection and feature projection techniques, PCA or LDAs, will be useful. So sometimes we can reduce our dimensionality and we will not just lose, but we will win some performance because some features can be rubbish. And actually, ensemble learning methods like boosting, bagging, and one example is random forest and coefficients. They are state of the art. So if we can outperform them, that's very nice. It's actually a good choice to get some nice results for competitions or for fun or new evaluations. So maybe that's a baseline for the papers. So I go through the case study in the next lecture. We'll kind of summarize all the 5 lectures before. And can you please prepare the questions regarding the data set for the survey? Because after that it will be probably more difficult occasionally for the actual survey presentation. So of course you can write to me, but if you have questions now, we can solve it now. I guess it will be at least 4 groups. So each group will have 15 minutes, I think. You can present a lot, talk a lot, and think what you think. About. Also, if you get some analytics from data, do some correlation analysis, also very nice. So especially it's interesting to see what difference between different cities. Do people behave different in different regions or similar? And so on. Anyway, I hope everybody will have fun for it. Short break.